All right, guys, let's talk about section 3.5, number 4. Section 3.5, number 4. All right, so 3.5, number 4 is making the comparison between implicit functions and explicit functions. So we're given the equation of a circle. Everybody's will be slightly different, but I'll just say x squared plus y squared equals 25. Okay? Now, if we all recall what that looks like, that is a circle. In fact, I just discussed this with my college algebra class yesterday. That is a circle with the center at the origin and a radius of 5. So, this is going to be a terrible circle, of course. There's the cliche, I'm not an artist kind of thing, but I'm definitely not an artist. So something like that. The radius 5. Now here's the thing. Okay, that's not a function. It doesn't pass the vertical line test. And the thing is, we have two options here for finding a derivative. Either we can use implicit differentiation, like we have learned about this week. We can find one derivative. That's probably the easiest way. The other way is to break this implicit relation into two explicit functions, and then we can find the derivative of both of those functions. Essentially, what we do here is we try to solve this for y. That's what it means to write it in explicit form. You take your original equation, solve it for y, so we could say that y squared equals 25 minus x squared. And then if we take the square root of both sides, we have to use the square root property, which says y equals plus or minus the square root of 25 minus x squared. Okay? Now, the thing is, that's two functions. There are two functions there. We have the function y equals the square root of 25 minus x squared. And we have the other function, y equals the opposite, so negative 25 minus x squared. Essentially what that does is it breaks this circle apart into two halves, an upper half and a lower half. So this explicit function right here, the positive square root of 25 minus x squared, that's the upper half. That's like this half right here. Okay? And this one, the negative portion, that's the lower half of the circle. So like this. Okay? So it takes two explicitly defined functions to convey the exact same information as that implicitly defined equation. So this right here, these two equations are giving us the same information as that one equation. Okay? Now here's the thing. If I want to find the slope, of a tangent line on this circle using the implicitly defined equation, then I have to find the implicit derivative. If I want to find the slope of any point on this curve using the explicit functions, I have to be careful about which function I take the derivative of. Because if I'm concerned about, say, a point on the upper half of this graph, I have to use this function. If I want to slope down here on the lower half of the circle, I have to be sure to use the derivative of this function. So we have to be careful about which one we choose. Here, I can get a derivative that works everywhere on the circle. But here, this derivative is only going to work on the lower half, and this derivative is only going to work on the upper half. Let's take the implicit derivative first. So, implicit differentiation, the first step says to take the derivative of both sides of the equation. So I take the derivative of the entire left-hand side and take the derivative of the entire right-hand side. Okay, we then have a property of derivatives that says if you take the derivative of a sum, you can break that apart and take the derivative of each term individually and then add the results. So we know that the derivative of x squared is just 2x. We're taking the derivative of x squared with respect to x. That's just business as usual, no issue at all. But when we take the derivative of y squared, we're taking it with respect to x, and that's a y variable. The variables do not match. So we have to say, take the derivative like we think that we should, 2y, but we have to be sure to multiply via the chain rule by a dy dx. Then of course we know that the derivative of a constant is 0. So that was the first step of our implicit differentiation process. The second step was to isolate the dy dx term. So take the dy dx term to the left-hand side, take everything else to the other side. So we already have the dy dx term on the left-hand side. Let's take everything else to the other side. So the 2x needs to go to the other side. So 2y times dy dx equals negative 2x. The next step was to solve for dy dx. Well, I suppose technically the next step was to factor, but the left-hand side is already factored. Factor out a dy dx. But there's only one term, so that's not needed. All we have to do now is solve for dy over dx, that is the derivative of y with respect to x, and we get negative 2x over 2y, otherwise known as negative x over y. So here is our derivative, the implicit derivative. Our implicit derivative. Okay? Now, we can also take derivatives of our explicitly defined functions. So this derivative works everywhere. If I want to find the slope here, I simply find the x and the y value of that point, and then I evaluate at my implicit derivative. It doesn't matter if my point is up here on the top half of the circle or down here on the bottom half of the circle. This derivative works for the entire thing. That is the benefit of taking an implicit derivative in this case. But if I want to just deal with all of the techniques that we have talked about before we reached implicit differentiation, we can take the derivative of both of those using the chain rule and get a derivative here that'll work for the top half and a derivative here that'll work for the bottom half. So let's see, what does the chain rule tell us about this? The chain rule tells us that that derivative, y prime, is equal to, okay, think about that being 25 minus x squared to the 1/2 power. Okay, in fact, I will do these derivatives on the other side to give us a little more room. So let's do this over here. So we can say that y prime, actually let's rewrite y first. Y is 25 minus x squared to the 1/2 power. Okay? That's just taking into account writing this in exponential form instead of radical form. Now y prime, using the chain rule, is going to be 1/2 times 25 minus x squared raised to the 1/2 minus 1 power. 1/2 minus 1 is negative 1/2 times the derivative of our inside function. The derivative of our inside function, well, the derivative of 25 is 0. the derivative of negative 2x, negative x squared is negative 2x. Okay? I then need to simplify that. Oh, I forgot my prime symbol there. So y prime equals, okay, I have a 2 and a 2. Those cancel out. And I'm left with a negative x on the numerator and a 25 minus x squared. I'll write it in radical notation like so on the denominator. So there is my derivative of this version, the upper half of my circle. If I took the derivative of this one, it would give us the exact same thing, except the only difference would be that I would first factor out a negative sign. So let's do that real fast. Here, I could say that y equals negative 25 minus x squared to the 1/2 power. I'm going to do the exact same steps, except to start with, I'm going to factor out a negative sign, essentially factoring out a -1 using the constant multiple rule. And I'll say that this is now equal to negative 1/2 times 25 minus x squared raised to the 1/2 minus 1 power, so negative 1/2 times, again, the derivative of the inside, which is negative 2x. But now when I simplify, I get positive x over the square root of 25 minus x squared. So notice here, I get two different derivatives, one for the upper half. So this derivative right here will work if I want to find the slope of any point on the highlighted green portion here. It will not work for the lower portion. Okay? This one right here, this derivative, will only work for the lower portion. It will not work for the upper half of that circle. We could write this in a more condensed form. We could say that in general, the derivative is equal to, we'll call it y prime, is equal to plus or minus x over the square root of 25 minus x squared. Y prime equals x divided by the square root of 25 minus x squared. Now here's the thing. I contend that this and this are equivalent. Okay? They're equivalent because we have a x on the top there. Now it is negative, but what happens here? That right there is how we solved for y with a plus or minus out front. Okay? So these two things are conveying the same information. I would say this one's more difficult to work with, I suppose. But you get the same final solution here, that those two derivatives are equivalent, except that this one, you have to be careful with. That is, you have to be careful about what point you're dealing with. For instance, let's say we want to find the, let's see here. We want to find the slope at this point right here. Okay, now what is that point? Now let's see about this. If it was a unit circle, that would be square root of 2 over 2, comma square root of 2 over 2. Now, is it the case that point right there would be 5 square roots of 2 over 2, comma 5 square roots of 2 over 2. Let's see. Does it satisfy our equation over there? If we take this and square it, take that and square it, do we get 25? Well, let's see. If you squared it, you would get the square root of 2 squared, okay, over 2 squared. So you have 2 over 4 will be 1/2, and then 5 squared. So you have 25 over 2 plus the exact same thing, 25 over 2. So you get 25 over 2 plus 25 over 2 equals 25. So yeah, that is a point on this circle. So let's say you wanted to find the tangent line, the slope of the tangent line right there. Well, you could certainly just go straight to your implicit derivative. We could say that dy dx at our point 5 square roots of 2 over 2, comma 5 square roots of 2 over 2 is, and just evaluate. Okay, well that's negative 5 square roots of 2 over 2 divided by positive 5 square roots of 2 over 2, which that equals negative 1. So that is our slope there. Now that makes sense because you would imagine a slope of that tangent line being about 1 right there. So something about, like that. If we wanted to find the slope of the tangent line, say right here, well that point right there, again coming off at a 45-degree angle here, or a negative 45-degree angle here, that's going to be 5 square roots of 2 over 2, comma negative 5 square roots of 2 over 2. Now, let me address the explicitly defined derivatives. So this and this. If I was going to find that slope that I just found using the implicit derivative, I would have to be sure, if I was going to use an explicit derivative instead, I would be forced to use this one right here. Okay? I would have to use that derivative because that is the derivative for the upper half. And this point here is on the upper half of the circle, so I'd have to use this. So I would evaluate y prime at 5 square roots of 2 over 2, comma 5 square roots of 2 over 2. And right off the bat, it's a little more algebra involved there. Not that it's necessarily difficult, but there's certainly more algebra. You'll get the exact same answer that we got here. You'll get negative 1, but it'll take a little more work. Okay, but let's say I want to find the slope of that tangent line right here. Okay. Well, if I was going to use the explicit derivatives, I would be forced to use this one because that derivative is the one that works for the bottom half of my circle. And that point right there is on the bottom half of the circle. If I'm using the implicit derivative, I can just use this without considering whether the point is on the upper half or the lower half. This derivative here works for all points. Again, that's the nice advantage of the implicit derivative. And I can see right away, if I evaluate negative x over y, if I plug in, substitute these 2 points, I'm going to get positive 1. So m for this one is positive 1, m for this line is negative 1. It would take a lot more algebra to evaluate. Again, here is my derivative, my explicit derivative for the bottom half of the circle. It would take a lot more work to evaluate that at those 2 points, especially with all the radicals involved. But evaluating my implicit derivative at that point is very straightforward. Okay, so I hope that kind of explains, some advantages and disadvantages of implicit and explicit derivatives. Previously, all of our equations that we have taken derivatives of have been explicitly defined. Always y equals something. Y equals x squared. Y equals sine of 3x. Y equals the natural log of x plus 2. Always y equals something. But now we have a whole new class of equations that we can work with where you get circles, ellipses, all kinds of weird curves, interesting curves that we can now take derivatives of if we use implicit differentiation. So I wanted just to show here how you can solve this particular derivative using implicit differentiation as well as explicit differentiation. Now that won't always be the case. This is a circle, so we can kind of work with it in both fashions. But we're going to deal with other equations that are much more complicated that we want to be able to solve for y. So we'll just be forced to use implicit differentiation, really no question about it. But here, conceivably, we could get the slopes of tangent lines over here using either implicit differentiation or explicit differentiation. Although I would say just use implicit differentiation because it's a lot easier in this case. So I hope that explains it. Again, that this is all about section 3.5, number 4. So if you have any questions about that, I hope this clears it up. If not, we can always talk about it next time we meet for class. Have a good weekend.